So hello everybody. I hope everybody had a good break. Let us start the next session. We have many sessions devoted to machine learning security. This is going to be machine learning security session 1, and we have 4 amazing papers to present. Or maybe I have to also present myself. My name is Alexander Dmitrienko, University of Würzburg. And yeah, the first paper is going to be presented by Kuishu Wu from IBM Research, and would be great to get the slides on the screen.
So I can using this one to control the slide, right? Or okay. Hi everyone. My name is Qiushi Wu, and I'm from IBM Research. And this work is actually a collaboration work between the University of Minnesota and IBM Research. And actually, I'm pretty curious that this work has been classified for the machine learning security, because this one is actually like doing some application of the graph neural network on some system security related task. And the motivation of this project is about accurately identifying the indirect call targets, because identifying indirect call target has always been a critical challenge, because it's a foundation of constructing the call graph of the program. And furthermore, by constructing a call graph, we can analyze the control flow integrity. We can do some program static analysis or do program dynamic analysis. And however, for different applications of the indirect call analysis or of the call graph that have different kind of requirements. For example, for the control flow integrity, it cannot tolerate the false indirect call target. It can tolerate false indirect call targets, but it cannot tolerate the false negative of indirect call analysis. And also, it needs scalability. And on the other hand, for the static analysis and also the dynamic analysis, it can tolerate some false positives or false negatives, and it also needs scalability. However, for the existing approaches, they suffer from the high false positive rate, or it suffers from the poor performance for indirect call analysis for large programs. For example, for the type-based approach, the good thing of type-based approach is that it has no false negative, and it's scalable for large program. However, it typically suffers from high false positive rate. And on the other hand, this is mainly due to some general types which make the type analysis less effective. The general types here means like some integer type or some void type, or like this kind of general types. And for the alias, and for example, for this function pointer, the console blank hook function pointer in the Linux kernel, because its return type and also the parameter type, both of them are integer, which makes the type analysis less effective. So the type-based approach will find more than thousands of target functions for this function pointer. However, in the kernel, it just has several true positives, which means that most of them are false positives. And for the alias analysis, it typically have a high efficient and precise within a limited scope. However, it's not scalable, which means that if you want to analyze some large program like the browser or like the OS kernels, it's actually not scale. And if you want to do some approximation with alias analysis, it will generating lots of false positives and also false negatives. Therefore, the goal of this project actually develop an indirect call analysis approach that will have less false positives and less false negatives, and also scalable for large programs. And the downstream application of our approach should be static analysis or dynamic program analysis. So how can we do that? At first, we have an observation here, which is that the target functions of indirect call typically share similarity of high-level semantic. So at first, we can define what is a high-level semantic. For example, here we have example function pointers in the Linux kernel, and if you look at the function, look at the name of this function pointer, you may find that okay, this function pointer should be like file related, and also read operation related, and also it may relate to some iterators. And we define this kind of behaviors or operations related things as some high-level semantics. Therefore, for example, if we use the type-based approach, and we can find these 4 potential target functions here. And based on the high-level semantic, we may know that okay, the first one and third one, they're likely to be a target function because they are, by the function name, you know that okay, they are read file and iterator related operations. However, for the second one and the fourth one, they're actually pretty unrelated because they are about some direct-to-IO related functions. So this is pretty like an observation of the function pointer and related target functions. So the next question could be like, how could we measure this kind of high-level semantics, or how could we measure the high-level semantics of code? We would like to argue that the high-level semantics of code are frequently hidden within the nested structures of types and also the nested structures of the functions. Here are 3 GPIO device data structures, and they have different names because they are used in the different scenario, but all of them are GPIO device data structures. We can find that they share the GPIO chip struct, and also they share the row spin lock. They also share the unsigned integer, which name is base. And also, if you look into this structure, you can also find that they share a variable named like ARQmask. And for the function, they also share this kind of nested similarity. For example, here are 3 release functions, model-specific release functions, and there's a media driver. And we can find that all of these 3 functions, they have key-free inside, and also they use the struct. They are CX state-related structs. Even they have some in detailed difference. However, on high level, they are pretty similar. So in this project, we would like to use a graph-based approach to capture this kind of nested information and further capture this kind of nested high-level semantic. How can we do that? We would like to introduce a graph named as representative abstraction graph. And this graph will include the information of the call graph of the whole program and also the nested type graph of the whole program. For example, here is this picture shows an example of the representative abstraction graph here. Including the functions and types. For example, if we find that, okay, the function 1 have called the function 2, function 3, and the function 5, then we can build some links between these functions. So there will be a directed edge from the function 1 to function 2, function 3, and function 5, indicating the caller and callee relationship. On the other hand, you can also find some types inside this graph. For example, you can find a type 1 and type 2 and type 3. And if we find that, okay, type 2 is included in the type 1 and type 3 is included in type 1, then there will be a directed edge between the type 1 and type 2 and also type 1 and type 3. Also, like if the function 1 uses type 1, then there will be a directed edge between the function 1 and the type 1. And furthermore, we use the existing graph neural network, GraphSage, to train on this representative abstraction graph. The high-level idea here is that we would like to aggregate the features information from the neighbors. Which means, for example, we can still using this graph. For example, for the function 1, because it's called function 2, function 3, and function 5, and also it's used a type 1. And this means that we would like to including the information from the function 3, function 2, and function 5 or aggregate into the function 1. Also, we would like to aggregate the information from type 1 into the function 1. And for example, for this specific type, for this struct type, GPIO device struct type, because it includes the unsigned integer, it includes spin log, this kind of types. So this kind of the information of this kind of types will be aggregated into this struct. And also for another GPIO device structure, it's actually similar because it can also be aggregated from the similar subtypes. And during the training, we can do this kind of aggregation iteratively, and finally we can get the embedding of every types and also every functions. And just like here, for the function is similar, like this init function had called the write function and print function, and also use these two types. So we will aggregate the information of these two types and these two function calls into this init function. And also for another init functions in the same module is actually similar. Okay, so until now we can go back to our previous question, like given a function pointer, for example, like this function pointer, and if we can already use a type-based approach to identify a list of potential target functions, then the next step is that how can we assess the likelihood of these functions being a real target or false target? To do this, we need an anchor function, which means that, for example, if we can get at least one real target function of this function pointer, then we can calculate the distance between this anchor function to this list of the potential target functions. And we can rank the similarity between the anchor function with the functions inside this list. For example, if we can find this anchor function, and furthermore, we can know that, okay, this function is more similar to the first and third function, and it's not very similar to the second and the fourth function. So we know that, okay, the first and third function could be more likely to be a target compared with another two functions. And here is the overview of our system. The first one is about collecting some abstract information, which means that we will compile the source code to the LVMIR, and also we are collecting the texture information, and also the function call information, and also type information. And we call this kind of information as abstractive information. Furthermore, we will build the call graph and type graph and merge them into the representative abstraction graph. And also, we will also leverage the descriptions of functions and description of types, and also the function names and this kind of textual information. We will using them to initialize the vector of each function or each type. And finally, furthermore, we will train the RAG, and we will get the embeddings of each function and also each type. And furthermore, we will using a scope-aware pointer alias analysis to identify the anchor function. And for this approach, we will use a scope-aware alias analysis and combine that with some name-based approach to match at least one anchor functions for each indirect call pointer. And furthermore, we use a type analysis collecting the potential list of the potential target function list of each indirect call. And furthermore, we do the similarity analysis between the anchor functions and also the potential target inside the potential list. And furthermore, finally we can know, okay, which functions could be likely to be a true positive and which of them are not like a true positive. And compared with the traditional type-based approach, we can reduce the, for example, for the Linux kernel, and if we cite the similarity as 90%, we can reduce the average number of target functions for each indirect call from 84 to around 10. And also, because we can change, because the precision, the false positive or false negative can be adjusted by changing the similarity, and here is the graph. And for example, for our work, when we achieve a 0.3% of false positive rate, and our tool will achieve about 15% of false negative rate. But on the other hand, if we change the similarity and we change the recall rate to about 99%, which means that in this kind of case, it's nearly no false positive, and the false positive with no false negative. In this case, under this case, the corresponding false positive rate will be about 60%. And for our tool, it takes about 7 hours to train the whole model and analyze the whole kernel. And also, I would like to mention that for training the model, it takes about 3 hours, and for analyzing the whole kernel, it takes about 4 hours. But on the other hand, after the kernel has been extended, we can also improve. We can also add more edges into our abstraction graph, and for those kind of cases, we don't need to retrain the model a lot, because we just need to add some nodes and also add some edges into the original graph. So which means that it can be it will not take lots of time. It will not always take lots of time when you analyze some new versions of kernel or new versions of some larger program. And also, we also try to evaluate the abstract similarity into other security-related applications. For example, we try to using that to identify some similar vulnerabilities caused by similar functions. Also, we try to evaluating how this kind of technique can improving the performance, like of directed fuzzing, or like improving the vulnerability reachability analysis. More detail can be found in the paper evaluation part. And here is the conclusion of this work. We analyze the abstract similarity of functions, and we developed a graph-based technique for indirect call identification. And also, we evaluate a list of security-related applications based on our approach. Yes, thanks for listening. And if you have any questions, please feel free to ask me.
Okay, we start with questions.
Hi, Yaniv, Columbia University. Thank you for this talk. It was really interesting. I'm wondering if you experimented or kind of thought about what are the differences between your representation to capture the abstraction or the semantics of the function and other representations suggested by others using data flow, all the others, kind of tracing.
Yeah, I think this is a very good question. At first, we also thought about like if we can evaluate the similarity between functions by using some traditional like approach. You know that people are evaluating the similarity of some traces or just analyzing the using some machine learning related approach to analyzing the embedding of functions. We find that the issue of this approach is that sometimes there are two functions. There are some functions in the Linux kernel. Their names are similar or the descriptions are similar, but their control flow are pretty different. However, so this is why we didn't including the control flow into our abstract similarity, because we find that they may call some similar functions. And as you see that there are 3 release functions. For that case, the control flow is similar, but for that case, you can find that they call 3 different state structures. If we don't analyzing that iteratively, which means that if we don't look into those structs, those kind of similarity may not be captured by our tool. Yeah.
Okay, thank you. I'll take it with you offline. Thank you.
Yeah, thank you.
Any other questions?
Yeah, I think.
Hi, I have actually 2 questions. What was the sampling strategy used for sampling the graph? Because I worked with GNNs, and if the graph and the number of nodes and edges is too high, then it's very hard to fit all of those in the GPUs, and you have to use different sampling strategies to extract the subgraph which you want to train on. And my other question is, what was the performance difference between using embeddings that were already extracted from Word2Vec or other resources and just randomly initializing them, because GraphSage would, in the end, learn the node embeddings themselves?
Yeah. I think this is also good question. Yeah, for the first question, like, yeah, indeed, we need to select which algorithm or graph neural network algorithm we need to use here. This is why we choose GraphSage, because GraphSage can handle this kind of large graph. This is the reason why we choose GraphSage here. And for the second question, we indeed did some evaluation, like we randomly initialize the vector of each node and compare with using the name-based approach or using description embeddings. That performance is actually pretty bad. Yeah, it's pretty bad than using the name-based approach. And I think the reason is because the function name and also struct name, and you can see that they are of course including some information of the code. So we think that we need to using this kind of information. Be compared with randomly initialize embeddings of each node. Yeah.
So I think we need to move to the next speaker.
Thank you.
Let's thank the speaker now.